Now we come to a very, very significant law in electrostatics that is called Coulombs law. In its impact, you can consider it to be equivalent to the Newton's law with masses, right? We have been saying that likes repel, likes repel, and unlikes attract. Okay, now that is a macro property that we saw, but what is the law that binds them? Okay, if they are repelling, they must be repelling with the force. If they are attracting, they must be attracting with the force. Now what is that force? That is what was defined by Coulomb in his law, which goes by his name, Coulombs law. Understand? And it is amazingly similar to the Newton's law of gravitation. What does Newton's law of gravitation say? That the force of attraction is directly proportional to the product of masses and is inversely proportional to the square of the distance between them. This also says the same thing. It says that the force of attraction or repulsion, the force of attraction or repulsion, okay. Now you must understand that in gravitation there is only an attractive force. There is no repulsive force, right? But here in charges, as this tells us, and the numerous experiments that we did with glass rods and the silk cloths and the ebonite rod and the cat's fur, we saw that there was also a repulsion apart from attraction. Now the force of attraction or repulsion is directly proportional to the product of the charges, to the product of the charges, and is inversely proportional to the square of the distance between them, square of the distance between them. Now since we are defining the force, and force is a vector quantity, so what happens? We should also be giving the direction, is it not? This is the magnitude. The direction of the force is along the line joining the two charges, is along the line joining the two charges. That is the direction, okay? So in a sense, we say let Q1 and Q2 be two charges and R be the distance between them, and R be the distance between them. Then what happens? Then, as per Coulomb's law, F is directly proportional to Q1, Q2. Okay? F is directly proportional to Q1, Q2, and it is inversely proportional to R square. It implies that combining the above two, F is directly proportional to Q1 Q2 upon R square. Currently we are talking about the magnitude, so I put a mod here, right? So I am talking about the magnitude. The direction part is separately ingrained into the definition. Okay, so is that, and when this goes away, a constant of proportionality by the name K comes in. Mod Q and Q2, because this is mod, right? So K is positive, R is positive, this is positive. So currently what I am saying, because Q can be positive or negative. So if it is one positive and other negative, then what happens? The product is a -1, and we'll see what that denotes, right? So it is Q1 Q2 upon R square, and K, the K is equal to 1 upon 4 pi epsilon naught. Where epsilon naught is equal to 8.854 into 10 to the power minus 12. Okay. Let us try to understand what is the unit of this K. What is the unit of this? And if you put in this value of epsilon naught here, then the value of K actually becomes a very simple thing, 9 into 10 to the power same thing. That is 9 into 10 to the power 9. What will be the unit of K? What will be the unit of K? K will be Newton meter square per Coulomb square. Is it not? So it is Newton meter square per Coulomb square. What is the unit of epsilon naught? Epsilon naught will go there, K comes down, 4 pi does not have a unit, so it will be inverse of this. Is it not? So it is Coulomb square per meter square per Newton. Correct? We get that? What?
Coulomb square per meter square per Newton.
Why not?
एक बार पर करने में मतलब डिवाइड बाय मीटर स्क्वायर फिर डिवाइड करें तो
No.
तो हमें सिर्फ पर मीटर
Per meter square Newton. Or but you see, Coulomb square per meter square.
पर न्यूटन तो फिर वो ऊपर चला जाएगा.
Fine, it's not per of this, so per. Okay, so understand. So that is what it is. The value of K is 9 into 10 to the power 9. So you put any Q. So let's do it with 1 coulomb each. If 1 coulomb is separated by a distance of 1 meter, what happens? F is equal to 9 into 10 to the power 9 into 1 upon 1 square. So that is 9 into 10 to the power 9 newtons. 1 coulomb of charge separated by a distance of 1 meter has a repulsive force, if both of them are positive, of 9 into 10 to the power 9 newtons, which is equal to equivalent to 9 into 10 to the power 8 kg weight. Is it not? Okay, 9 into 10 to the power 8 kg weight, which is 900 million kg. It's not 900 million kg, or you can say 9 into 10 to the power 5 ton weight.
1 coulomb is separated by what?
1 meter.
मतलब किस चीज से सेपरेट कर रहे हैं?
No, they are placed 1 meter apart in vacuum.
1 coulomb.
Yeah, 1 coulomb and 1 coulomb, right? So it is equivalent to 9 lakh ton. You understand? That kind of weight it has. Weight due to a body which is 9 lakh tons or 900 million kg, 0.9 billion kg. So huge amount of force, huge.
So 1 coulomb does not exist.
So no, it exists. 1 coulomb of charge, 1 coulomb of charge is a huge amount of charge. Let us take 200 ml of water. 200 ml of water will be 200 grams of water. Is it not? 1 meter cube, 1000 liter is 1000 kg. Okay, so 200 grams. And how many moles of water is this? So it is 20 upon 200 upon 18, no? The molar mass of water is 200 upon 18 is how much? Is how much? 1, 2, 1. Okay. 11. Mm, 0.1 mole. Excuse me. It will keep on continuing, no? It will keep on continuing. 11.1 mole. Now that means what? It means what? It has 18 protons, 16 protons in an oxygen, 16 protons in an oxygen, 1 proton here and 1 proton there, here. So 18 protons. So it is 18 proton in one atom, 18 protons and 18 electrons. Right? And so many moles. So total 18 into 11.1 mole of proton and 18 into 11.1 mole of electron. It's not? Now 1 mole, so what is the total charge? It is 18 into 11.1 into 1.6 into 10 to the power minus 19 into 6.02 into 10 to the power 23. Get that? This is how much? 10 to the power 4. This I approximately take as, this is 9.6 something. Charge on that proton. I want to know how much charge is a glass of water carrying, a cup of water carrying. How? No, wait. What is the positive and negative charge contained in a cup of water? So 10 to the power 4. This I take as 9.6, but let us take it as 10, okay? And this instead of 11 I take 11.1 I take 11, so it is 198. So 198 into this. That makes it 1.98 into 10 to the power 7 coulombs, which is approximately 2 into 10 to the power 7 coulombs. A cup of water or a small glass of water contains 20 million coulomb of positive charge and 20 million coulomb of negative charge. Understand?
This is exponential. These are 14.
So, and it is all in a cup of water, right? If by any chance they get separated, it will be kind of a nuclear explosion right in front of your eyes. Right? And you are fortunate that it is not happening. Right? You can understand the tremendous force. What will be the dia? Hardly 5 centimeters. Not even that. Okay, and this kind of charge, even for a fraction of second, if it gets separated, it will be a pure and total havoc. Understand? So that is the kind of charges that are moving around you, and we are not aware. So you're gulping down, say, this kind of charge every moment you take a glass of water, without even realizing what we are doing. Okay. So do we understand what is being said? So this is the law that actually quantifies the force. However, in this format, the format in which we have written it, it does not give you the direction. Okay, it does not give us the direction. Understand?